z equals f of xy equals x squared plus 2y squared minus xy minus 7x. There's a point that we're thinking about as well, a point P, whose x and y coordinates are both, well, no, one's 4, the x coordinate's 4, the y coordinate's 1. Let's think about what we know so far. We can, for example, take partial derivatives of this. Once again, you should be comfortable with any of the notations for these partial derivatives. I might use any of them. We could use dz dx notation, partial z, partial x, z sub x, or we could use partial f, partial x notation, or f sub x. Probably the best notation to emphasize that this is a function of x and y is this last notation. Differentiate it by treating y as a constant, which reminds me, you should be able to do it with a limit as well. You should be able to calculate this, yes, one more time in your life at least, as a limit if I asked you to. It would be a limit as h goes to 0 of a difference quotient. It's always an h on the bottom, right? It's always a change in the function value up top. F of something minus f of something else. The starting point is xy. That's the coordinates that go there. The ending point for differentiating with respect to x is a point whose coordinates change x a little bit, but not y. X plus h, comma y. So if I asked you to do this derivative as a limit, you should be able to. Will I? I don't know. I haven't written the exam yet. Very typically, maybe not, but I'm not ruling it out. Okay, it's something you should know for the test. But anyway, you also should be able to do it in the ordinary, simpler way, treating y as a constant. You'll get 2x plus 0. Right, this is not like implicit differentiation in Calc 1. We're not assuming y is a function of x. Minus, careful there, that's the trickiest one. Differentiate with respect to x, treat the y as a constant, get minus y. I even make mistakes sometimes. I got to be careful. Minus 7 simplifies to 2x minus y minus 7. Partial with respect to y with all its various notations. Not that you have to rewrite all these notations every time. If we were doing it as a limit, it would be a similar limit, except it would be y changing instead of x, y plus h instead of x plus h. Otherwise, it's pretty similar. But to do it, treat x as a constant. X squared differentiates to 0. 2y squared differentiates to plus 4y. Minus xy differentiates with respect to y to minus x. And then that differentiates to 0. If I put x first and y second, I could write this as negative x plus 4y, but that doesn't matter. I also can write it as 4y minus x. You should be able to, of course, then evaluate these partial derivatives at the given point and technically interpret their meaning if I asked you to interpret their meaning. Fx at the point 4, 1 then. Look at this formula, plug in x equals 4 and y equals 1. And amazingly, we get 0. I didn't expect that, but that is what we end up with. It's a book problem, so sometimes they do that. Plug in 4, 1 into this one, we're also going to get 0, it looks like. Negative 4 plus 4 is 0. So what does this mean? Textbook did this on purpose. It means if you graph this function, it's going to be a surface in three-dimensional space, probably both partially above and below the xy plane, where z is 0, because I got positive coefficients and negative coefficients there. These rates of change correspond to rates of change in the X and Y direction is if I slice the surface with vertical planes. Dare I try to draw this? I'm gonna draw a graph, but it's not necessarily going to be the true picture. In general, I've got some sort of surface here, some sort of weird bowl shape, maybe. Could be above the XY plane in general. I got this point P and a corresponding point on the graph itself, whose third coordinate is Z equals F of P, if P has coordinates X, Y. As a three-dimensional point, its third coordinate would be 0 if it's in the XY plane. This point as a three-dimensional point would have coordinates X, Y, F of X, Y. And when I find a partial derivative with respect to X, I'm treating Y as constant. So that means I'm slicing it with planes perpendicular to the Y-axis, where Y is constant. And I'm going to get maybe some sort of curve like this, parallel to the XZ plane. And the derivative with respect to X is going to be the slope of the line there, which in this drawing would be a positive slope, even though as a two-dimensional picture, it looks like a negative slope, because you got to imagine coming out of the screen. As X increases, you're moving toward you. I made the function be going up there as X increases as you move toward you out of the screen. And the partial with respect to Y would be slicing it with planes perpendicular to the X-axis, parallel to the paper. And you're going to get a curve, say something like this maybe. And partial with respect to Y is measuring that slope there. Let's also evaluate this at some other point, so we get something more interesting for example, to do a linear approximation. Let's pick some other point Q to be like, well, let's pick, how about XY equals 1, 2. Let's just see what the partial derivatives are there. Fx 1, 2. There's the formula for Fx, 2x minus y minus 7. It's going to be 2 times 1 is 2, minus y is minus 2, minus 7 is negative 7. Fy 1, 2, looking right here, is going to be negative 1 plus 8 is positive 7. I didn't mean to have those come up to be opposites. Say I was after a linear approximation to this function near this point in question. Say I was wondering, could I figure out f of 1.2 comma 1.7 without technology? We could think of it as f of 1, 2 plus fx 1, 2, the partial with respect to x at 1, 2 times delta x, plus fy 1, 2 times delta y. Here is the formula for f. So f of 1, 2, and we could call this thing, we could give this a name, we could call it L of xy for linear function. It's a linear function of x and y. Delta x could be thought of as x minus 1. Delta y could be thought of as y minus 2, using the point with coordinates 1, 2. What's f of 1, 2? Plug in x is 1, y is 2 here. Get 1 squared is 1, and this is going to give me an 8. 1 plus 8 is 9. Minus 2 is 7. How about that? Minus 7, 0. This is just so unbelievable how I keep getting zeros and other coincidences. Did I do that right? 1 plus 8, 9 minus 2. Yeah, okay, that's a 0. It's not typically a 0. Then minus 7 times x minus 1 plus 7 times y minus 2. I'm evaluating this at xy is 1.2 comma 1.7. So I get negative 7 times 1.2 minus 1 is 0.2 plus 7, y minus 1.7 minus 2 is negative 0.3. So it looks like I get what would it be? Negative 1.4 minus 2.1, negative 3.5. It's my approximation for f of 1.2 comma 1.7. Let's just double check all this stuff. So that's you could call that a tangent plane approximation. Here's how you could double check the derivatives if you wanted to with a capital D. You could type in the L of X function like this. F of 1, 2 plus, okay, let's call this Fx. Fx 2x minus y minus 7. Fy negative x plus 4y. Then I could do this to define the L of X function. Oops, that should be a 2 there. And let's double check that I got the right thing. So I'm approximating f of 1.2 comma 1.7 using L of 1.2 comma 1.7. Yeah, not too terribly far away. And that's what I got by hand, negative 3.5. So it looks like I did it right. As far as the equation of the tangent plane goes, I mentioned this Friday before break, there's that kind of crazy looking equation in the book that involves a normal vector. You don't need to be so fancy. Effectively, the equation of the tangent plane is z equals that. Z in this case equals, I'll put the 0 in there for emphasis, 0 plus minus 7 times x minus 1 plus 7 times y minus 2. That effectively is the equation for the tangent plane. To put it in more of the standard form, like the book says, essentially just subtract z from both sides. And you write it as negative 7 times x minus 1 plus 7 times y minus 2 minus z equals 0. In general, what you have here is typically written in the book as a minus in parentheses z minus f of x0 y0. But our f of x0 y0 in this problem was 0. So we didn't need it there. I think it's easier to think about the tangent planes in terms of a linear approximation. This did tie into ideas about differentiability. One thing about differentiability to know is that the function will be differentiable at a given point, like 4, 1 or 1, 2, if those partial derivatives exist there and are continuous functions near those points. No problem with that. These are definitely continuous functions everywhere. Most examples we encounter, it's not going to be a problem. The partial derivatives do exist, and they are continuous functions near any given point in the domain. So differentiability is going to hold. The more technical way to talk about differentiability was in terms of good linear approximations involving the differential idea, infinitesimals. You don't have to know the full abstract idea of differentiability, but you should feel comfortable with the differential notation, dz, dx, and dy, those things. I mean, we can even apply it in this exact same problem. Effectively, it's just another way to think about the linear approximation with different symbols. In the general case, one way to think about linear approximation, if you're approximating this function, z equals f of xy, approximate such a function near some point xy equals ab, say, what we just did, we thought about the linear approximation this way. F of xy is approximately L of xy, where L of xy is f of AB plus f x AB times x minus a plus fy of AB times y minus b. That's what we just did with the example. You should feel comfortable thinking about this another way. Subtract f of AB from both sides and write it like this. F of xy minus f of AB is approximately this. You should also feel comfortable writing this with delta notation. Delta z is approximately this. Partial derivative with respect to x at the point times delta x plus the partial with respect to y at the point times delta y. And you should feel comfortable thinking about this with the d notation. dz equals, not approximately equals fxab dx plus fyab dy. Effectively, in going from here to here, we are letting dx be delta x and dy be delta y, but dz is not delta z. That's maybe worth emphasizing with a but dz is not delta z. Instead, they're approximately equal. And maybe a better way to say that is delta z is approximately dz, where dz is defined by this equation. Now, there's lots of different ways of thinking about this equation. We are effectively treating dx and dy as new variables. And dz is another new variable defined in this way. It's almost as if you could think of it this way. In this picture here, you could imagine translating the entire three-dimensional coordinate system to this point right here, redraw the axes, but label them differently. Label the one coming out this way dx, the one going this way dy, the one going this way dz. That is one way to think about what we're doing here. Another way to think of it is to imagine these things to be what are called infinitesimal quantities. Infinitesimally small, smaller than any positive number you can think of. Of course, that's actually nonsense. In the standard real number system, at least, there's actually something called non-standard real numbers, hyper real numbers, where it isn't nonsense. But that subject is so hard. I found a book on it in the library once. I opened it up, started trying to read the first page for about a minute. I put it back, never to be looked at again. Okay, it's hyper real numbers and non-standard analysis is super duper hard. We don't want to do that. We want to think of, if we think of these as infinitesimal quantities, we want to just think of it intuitively as really tiny numbers. Like how tiny? Way tinier than 10 to the negative 100 power. Okay, unimaginably tiny. It's an intuitive thing. For what reasons? Because it's useful for understanding, believe it or not, especially when we get to integration. Thinking about these as infinitesimal quantities from an intuitive standpoint can be helpful. That's why we do it. You also call them differentials, and thus the name. In fact, this is called the total differential. So they have a couple different names. They're called infinitesimals when you think of them as infinitesimally tiny numbers. You call them differentials as well, because then it's a bunch of D's. D for differential. It's related to differential calculus. That's another reason you can call them differentials. The book, it gets a little crazy with these things when they talk about the differentiability idea. Kind of go overboard with it. I don't want to go overboard with it. I just want to think of it intuitive. But something new now related to section 12.6 is to relate these things to something called directional derivatives as well in gradient vectors. This expression here could be thought of it as a dot product. Why? Because it's a sum of products, just like dot products always are. This could be thought of as the dot product of the vector fxab, fyab, with another vector whose components, I guess, are dx and dy. Kind of a weird thing to do, but it could be thought of that way. dz could be thought of as that dot product. And in particular, this vector here is a special vector. It's a vector whose components are the partial derivatives with respect to x and y. It's called the gradient vector of f at AB. And it's got notation, a special notation, an upside down delta, if you like, f of AB. Could call it del if you like. I've seen it called nabla, though people don't typically say nabla. Some people just say D, some people just say gradient. That's actually what I usually say is gradient. The gradient vector of f. So it's a vector, it's an arrow. In section 12.6, it's used to compute something called a directional derivative. If you've got a unit vector, remember what that means, length equals 1, you can find the derivative of your function f in the direction of that unit vector. What if it's not a unit vector? What if you're trying to find the derivative of a function in the direction of some vector that's not a unit vector? Well, you just find a unit vector in the same direction. Normalize the vector. DUF at a point AB is called the directional derivative of f at AB in the direction of u. Why does u have to be a unit vector for this to work? Is because you want to think about, you want derivatives to be rates of change, right? You want to think about this as being a rate of change of the function in the z values as you change x and y in a certain direction at a unit rate, you might say. And you can define this with a limit, and you'll see that in the reading. But certainly for the purposes of the exam, at least, and I think on the homework too, there's a better way. There's a better computational method. The way you compute it is you calculate the gradient vector at the point and dot it with u. Just do a dot product, which has the benefit of also being able to interpret it geometrically. That's the same as the magnitude of the gradient vector at the point times the magnitude of the unit vector at the point times the cosine of the angle between them. But u as a unit vector, that's 1. So this is just the magnitude of the gradient vector times the cosine of the angle. For our example, for z equals f of xy equals x squared plus 2y squared minus xy minus 7x, at, let's say, the point Q, which was 1, 2, in the direction of, let me pick a non-unit vector, direction of v equals, say, 3, 4, how would I find the directional derivative? The first thing to do is to find a unit vector in the same direction as v by dividing v by its magnitude. Oops, I need pointy bracket notation. Divide v by its magnitude. The unit vector in the same direction here is pretty simple. It's just that. What's the gradient vector? In general, it's going to be 2x minus y minus 7 for the first component and negative x plus 4y for the second component. The gradient vector evaluated at the point Q, 1, 2, then will be what we got before, negative 7, positive 7. And therefore, the directional derivative in the direction of the unit vector u, which is the same as the direction of the non-unit vector v, is the dot product negative 7, 7 with 3/5, 4/5. That'll be negative 21 over 5 plus 28 over 5. And that'll be 7/5 or 1.4. That is measuring the slope of the surface. Imagine the surface, that's the graph of this function, above the given point 1, 2, in the direction of this vector u. So you got to imagine an xy plane and drawing that vector u in that xy plane, and that corresponding to cutting the surface with a plane parallel to that vector. And you're going to get a certain slope in that direction. It will be 1.4. So I think for the exam, I'm not ruling out being able to compute something like this. It's a pretty straightforward calculation. As far as the homework on Friday goes, there's also interpreting the gradient vector in some other ways based on the fact that this directional derivative equals this. Interpreting the directional derivative as well. Where is this maximized? In what direction? It's going to be maximized where the cosine of the angle is 1. The cosine of theta, the angle, is going to be 1 if theta is 0. If u and the gradient vector are in the same direction. And it's going to be minimized if the cosine of the angle is negative 1. If they're in opposite directions, if the angle is 180 degrees. I'm talking about u with the gradient vector. What's the relationship between these two vectors? What that ends up meaning, you'll see in the reading, is if you make the level curves of the function, and f is, say, increasing as you move up this way, and you're at a given point AB, turns out the directional derivative is perpendicular to the level curve at that point and points in the direction that f increases. And that's the direction that the function increases the fastest near this point. I draw a right angle there. That means it's a right angle with a line tangent to the curve right there. So that's in the reading. I'm not going to test you on that for Wednesday. But you should be able to do a basic directional derivative calculation like this. I think it's simple enough that I can maybe put that on the exam. All right. What else could be on the exam? Let's go back to curvature and acceleration vectors. Crazy kinds of formulas. Let's review those formulas, and I'll show you an exam question that I had in a sample exam. We'll also look at one of Dr. Yang's sample exams here quickly. And just try to, without going through every detail, try to get a basic idea of how these problems would go. For example, on a sample exam that I have, exam 1 from a few years ago, spring 2018, I had a problem like this. So my function, f of x equals x squared, generates a parametric curve here. I'm using x as the parameter instead of t. I could have switched to t. Don't let it bother you that I kept an x here. It does make using this formula maybe a little simpler to think about, is I think the reason I kept it as an x. But this is a parametric curve. X is the parameter. Let's just quickly review, without doing the details, how to find things like the unit tangent vector, unit normal vector, find the curvature. We didn't really talk about the center of the osculating circle, but we should be able to find the radius of it. And also talk about decomposing the acceleration vector. See if we can do this, the big idea here quickly. So I got, again, y equals f of x. And that's generating a parametric curve. Let me go ahead and switch to t on the paper here, okay? R of t equals t comma f of t. It doesn't matter what you call the variable. I call it x on the exam, I'm calling it t on the paper. It's not a big deal. What kinds of things should you be able to do? You should be able to find the velocity vector. V of t is the derivative of the position vector. And for an example like this, the first component's simple. It just differentiates to 1. Second component is f prime. And the acceleration vector is going to be the derivative of the velocity vector, which is the second derivative of the position vector. And for this kind of example, the first component is going to be 0. For other kinds of examples, it won't work out like this, right? This is a special kind of example where the first component here is just a t, making its derivative 1 and its second derivative 0. That doesn't always happen. We're talking about the parametrizing the graph of a function here, an ordinary function as a parametric curve. Very special kind of problem. You should be able to find the speed, maybe cursive v, if you want to use that notation, as the magnitude of the velocity vector. In other words, the square root of the velocity vector dotted with itself, which for this example will be square root of 1 squared plus f prime of t squared. It doesn't always work out like this. That's the speed. The unit tangent vector, capital T, is, you might say, the normalized velocity vector. You want it to still be tangent to the curve. The velocity vector, when it's non-zero, is tangent to the curve. So divide by the velocity vector by its length, divide the velocity vector by the speed. So for this example, that's going to simplify to this. And again, more specifically for the exam problem, f of t was t squared. So f prime of t is going to be 2t, for example. So I'm doing a bit more general here. And this is a function of little t. You can plug in a number to find a specific unit tangent vector. Should be able to draw a picture to interpret it. It is a unit vector, as long as you're not dividing by 0, as long as the speed is non-zero. It's a unit vector pointing tangent to the curve, length 1. Its formula typically will be complicated because of the square roots. Unit normal vector, n of t, is a normalized version of the derivative of the unit tangent vector. Take the derivative of the unit tangent vector and divide by its length, which you could see is going to be kind of crazy complicated in this situation. However, I did mention this in class. There's a trick when you have a two-dimensional problem. This was also in the book. When you have a two-dimensional problem, you know t and n are orthogonal to each other. Their dot product is 0, and they are both unit vectors. And so what you can do in 2 dimensions is you can swap the coordinates and put a negative sign in front of the appropriate one based on a picture. I did mention this. What kind of picture would be helpful here? If f of t is t squared, we're really parametrizing a parabola like this. Say t is positive. If we're at, say, this point right there at some moment in time, the unit tangent vector is going to look like this. The unit vector, unit normal vector, here's the key thing, points toward the direction the curve is curving, since it's related to the rate of change of the unit tangent vector. It's as if you imagine driving along a curve like this in your car, you're turning left slightly the entire time. You're curving toward the leftward direction. the unit normal vector's got to point this way. So if the unit tangent vector happens to have components AB, which are both positive in this case, the unit normal vector therefore has to have components negative BA, where the first component's got to have the negative sign because you can see it's pointing to the left. If the curve was curving the other way, and this had components AB, then the unit tangent vector is going to point this way, and its components would be B negative A. You swap the components and put the negative sign in front of the appropriate one for two-dimensional problems. What about acceleration vectors? Well, obviously, again, you can compute the acceleration vector this way, but more important for us was decomposing it into tangential and normal components. A equals A sub t times capital T plus A sub n times capital N, where you got to figure out what those things are. And there are a bunch of kind of crazy formulas for those. Actually, the AT was simpler, two simpler formulas. This box was on page 669 here. You can compute AT, the tangential component, either as that dot product or as that derivative. And notice that's the derivative of the speed. Magnitude of the velocity vector. For the unit normal, the normal component, you can do this dot product, or that square root, or that ratio involving a cross product, or that thing. Which of them is typically easiest? I think these two middle ones are typically the easiest ones. I would most typically say default to this one for a two-dimensional problem and default to this one for a three-dimensional problem involving a cross product. Which does bring me to wanting to show one of Dr. Yang's problems from last fall. He did do a three-dimensional problem. And I guess I'm not ruling it out. He actually gave it as a velocity vector, not a position vector to start with. You could integrate that to find the position vector if you also knew the initial position. And in fact, that's what part A was to do. Okay, that was on his exam too. You could integrate component by component and then use the starting location to figure out what the constants of integration are to figure out your position function. That technically was what I said was maybe could be on our exam one, actually. Integrate that. Integrating 4 cos t would give you 4 sine t. Sine of 0 is 0. So if your initial x coordinate is 2, the first component would be 4 sine t plus 2. Second component, you have to integrate this to get negative 5 cosine t. Cosine of 0 is 1. Negative 5 times that would be negative 5. You want to be at 2. You'd have to add 7, I guess, to that. Negative 5 cos t plus 7. Integrate this one to get the third and fourth. I think it's simple enough, but I guess I would say I'm not ruling that out either. It technically was something we covered before the first exam, I think the day before the first exam. Acceleration is just the derivative of the velocity. I guess this particle is a smiley face. Unit tangent vector. Velocity vector divided by the speed. You got to find the speed. It'd be the magnitude of this. It'd involve a square root of a sum of squares, probably cos squared t plus sine squared t equaling 1, makes it something you could simplify a bit more. Would it really simplify? It's not so clear, actually. Unit normal, the curvature of the path. I forgot to mention formulas for curvature in section 11.5. This is one. So he had them do this one for the formula for the curvature that did involve a cross product. So it's the velocity vector cross the acceleration vector, take its magnitude, divide by the speed cubed. R prime is V, R double prime is A. This is the speed cubed down there. That's probably the easiest formula. Should be able to evaluate the curvature at any moment in time. The radius of curvature is 1 over the curvature. Like if the curvature is high, it's a tight curve, like a small circle. 1 over the curvature would be small. The radius of curvature would be small. If the curvature is small, it's a very big circle. 1 over a small number is a big number. Radius of curvature is large. Had a length of path problem as well. Okay, I'll have to think about this, and maybe if I share this with you, like, say, are there things here you should be able to do? I guess we did talk about arc length. I was thinking that was before the exam one as well. So anyway, start looking at those old exam problems. I'm going to be writing the exam tomorrow. I'll try to get up some answers on Moodle for sure tomorrow. Maybe some today if I have time. It's certainly the subjects we've covered since the last exam, but evidently maybe a little bit more, maybe like change in position or find a position function if you know the velocity, that kind of thing. Arc length could be on there. All right. Limits, continuity with simple examples maybe too. I should also mention second order partials too, and the fact that you can do it in either order.